So it's a great pleasure to welcome you all to the today's edition of the ENLA seminar. Today we have Nikhil Srivastava from UC Berkeley with us. It's a great pleasure to have him here. He got the PhD in 2010 at Yale with Dan Spearman on spectral sparsification and restricted invertibility. Then after stays at Microsoft Research, Princeton, MSI, etc., he became an assistant professor in Berkeley at Berkeley in 2015, where he is now associate professor. His research touches on a lot of topics, in particular in theoretical computer science and linear algebra, as you already can see from the title. And he's probably most famous for solving jointly with Adam Marcus and Dan Spearman the Cadison-Singer conjecture. And he was awarded the Sine Polya Prize in 2014, was an invited speaker at the ICM in 2014, and received the Michael and Sheila Held Prize in 2020. So it's a great pleasure to have you here. Nikhil, please go ahead.
Thanks a lot, Daniel, and thanks very much to the organizers for inviting me. Okay, so this talk is called Pseudospectral Shattering and Diagonalization in Nearly Matrix Multiplication Time. And it's based on joint work with my current and former graduate students, Jess Banks, Jorge Garza-Vargas, Urjit Kulkarni, and Shautagi Mukherjee, who are pictured here. So the talk is about the computational problem of diagonalizing a matrix. So in this problem, we're given a square complex n by n matrix A, and you want to find an invertible matrix V and a diagonal matrix D so that A is equal to V dV inverse. So of course, as stated, this is not a legitimate computational problem because, well, okay, not all matrices are diagonalizable. And also, you can never solve this problem exactly in a finite amount of time because you can't compute the eigenvalues exactly. So what we really study is an approximate version of this problem. And I'm going to study the approximate version in this box. So given an n by n complex matrix A and a desired accuracy delta, we want to find V and D so that the operator norm of A minus V dV inverse is small. So it's less than delta times the operator norm of A. So this is called a backward error formulation, which means that given an input A, you don't solve the problem for A, you solve a nearby problem exactly, and how nearby is determined by this accuracy parameter delta. And this is the standard notion of error in scientific computing. And as I'm sure people in this audience know better than I do, if you have a well-conditioned problem, then having a good backward error implies a good forward error as well. So that's the statement of the problem. So any questions about the statement? Okay. So this still doesn't. Okay. So our goal is going to be to develop provable algorithms for solving this problem on every input A. And we're going to be interested in the complexity of such algorithms. And to talk about complexity, we need to specify a model of computation. So I'm going to do that now. So there are many models of computation that could be studied. So maybe the most sort of abstract model is exact arithmetic, in which you assume that you can store real numbers on a computer exactly, and it takes unit cost to do arithmetic with them. So this is the standard notion in, let's say, algebraic complexity theory. But of course, you can't actually store real numbers on a computer. So maybe a more realistic notion is rational arithmetic, in which numbers are stored as rationals, so numerator and denominator. And now the cost of doing arithmetic with these rationals depends on the number of bits in the numerator and denominator. And typically, for an n by n linear algebra problem, the numbers involved themselves are, have polynomial in n bit length. And so the cost of arithmetic becomes polynomial in n. And this model of computation is sort of common in the symbolic computation or theoretical computer science community. And then the last model, which is the one that's used in numerical analysis, is finite arithmetic, where we assume that we round all numbers to b bits of precision, where B is ideally, some very slowly growing function of n and delta, let's say polylog n over delta. And so what this means is that, you don't perform arithmetic exactly. So for example, in floating point, if you add two matrices, you don't actually get to add them exactly. You compute their sum, but multiplicatively perturbed by 1 plus E, where E is some matrix whose entries are bounded by 2 to the minus B, where B is the number of bits of precision. And you could also define models where the error is additive. In this talk, all the numbers involved will be in a small enough range that additive and multiplicative are equivalent. And to simplify the exposition, sometimes I'll use additive errors. But this is finite arithmetic. And the advantage is this is closest to what's used on actual computers. And of course, arithmetic is much faster. It takes polylog n over delta bit operations for a pair of numbers. So those are the three models of computation. And let me review what's known about this approximate diagonalization problem in these models. So for the case of general matrices, the first provable result for all matrices is due to Jin-Yi Tsai from 1994 in the second column. And he proved that in rational arithmetic, this problem is in polynomial time. So what he proved is given such a matrix and desired accuracy, if you know that the matrix has entries with little a bits, has integer entries with little a bits, then you can solve this problem in time that's polynomial and n log 1 over delta and this number of bits per entry. And I should say that this actually gives something, this gives something stronger. This gives a forward error solution, but in particular, it solves this problem. And for a couple of decades, it was open whether there's a provable algorithm for this problem that works in finite arithmetic. And that problem was solved by Armentano, Bergesser, Beltran, Cooker, and Chubb in 2015. And they gave an algorithm which solves this problem in order n to the 10 over delta squared arithmetic operations with this polylogarithmic kind of precision. So that's what's known about the general case. And this might be a little bit surprising because we kind of diagonalize matrices all the time on our computers. And maybe part of the reason many of us don't see the difference is that for Hermitian matrices, much better theoretical provable results are known. So in particular, there's this famous work of Wilkinson, Decker and Traub, and Hoffman and Parlett from the 60s and 70s, who showed that shifted QR solves this problem for Hermitian matrices in time that's n cubed plus n squared log n over delta with logarithmic precision. So this is a summary of what's known about this problem. So any questions about this?
I think Cleve has got a question. Cleve?
Yes. Oh, should I look at the chat? Okay. What about 0100? You mean the Jordan block? Yes. So this question is still well posed.
Can you hear me?
Yes, I can hear you.
Yeah. Yes.
It's one of my rules of computing is you should not try and compute something that doesn't exist.
Mm-hmm.
Now,
right. So
what about you're going to get to this, right?
I'm going to get so as stated, if you give me a Jordan block, this problem has a valid output, right? Namely, I can output the diagonalization of a nearby matrix.
Well, but the V is if it's nearby, V is not well conditioned.
Well, we actually proved that there is a nearby V that is well conditioned. So I'll get to that in a moment. But even for Jordan block, okay, it turns out there's a nearby V there's a nearby matrix for which V is well conditioned.
I'm not worried about Jordan blocks per se. I'm worried about matrices that aren't diagonalizable. But okay, go on.
Right. So it's a very good point. But what we prove is that for every matrix, there's a nearby matrix which is diagonalizable, for which V is well conditioned.
Okay, so there are no more questions on the chat.
Okay. So so what's the result? The result is here. So there's a randomized algorithm which solves this problem for every matrix A using n to the omega plus little of 1 times log polylog n over delta bit operations in finite arithmetic, where the number of bits of precision is log to the 4 n over delta. And implicit in this theorem is, that the V that's output has a good condition number. The condition number is polynomial in n over delta. So in particular, it proves existence of, a nearby matrix with a which is diagonalizable with a good condition number. And it's a randomized algorithm, so that means it succeeds with high probability. And here omega is the exponent of matrix multiplication. So so here are some comments about the theorem. So the first thing is it's actually a reduction. It shows how to solve this problem using log squared n over delta approximate matrix multiplication. So if you give me a black box that does numerically stable matrix multiplication, I can turn that into a diagonalization algorithm by calling it log squared n over delta times. The algorithm itself is largely not new. It's a variant of an algorithm called spectral bisection from 1974 of Beavers and Denman. But it has one important new step, which is uses random matrix theory. And finally, if you care about just complexity estimates, then this improves the running time even for Hermitian matrices and for singular value decomposition, for which the previous best provable exponent was 3. So that's the statement of the result. Any questions about the statement?
No, I don't see any question here.
Okay, so before telling you the proof, let me try to explain what, at least to me, makes this problem hard, or what are the difficulties. So I'll show you 2 examples. So the first example is due to Mark Embry. So this is a tridiagonal Toeplitz matrix. It has distinct real eigenvalues that are, fairly, they look pretty harmless. But actually, its eigenvectors are highly non-orthogonal. And as a result, you can check that the eigenvalues are highly unstable under perturbation. So if you perturb this matrix A by some E, then the eigenvalues can move by as much as 2 to the n times the norm of E. So the phenomenon here is that this matrix has highly non-orthogonal eigenvectors, and this leads to instability of the eigenvalues. Here's example 2. This is taken from a paper of Parlett and Liu from 1992. This is a symmetric tridiagonal matrix. Again, it has distinct real eigenvalues. The issue here is that some of the eigenvalues are very, very close to each other. And as a result, for a certain regime of perturbations, the eigenvectors can be highly unstable. So if you perturb this matrix by some E, then it turns out that there are eigenvectors that can move by n factorial times the norm of E for a certain regime of perturbations E. And essentially the reason is that these eigenvalues can collide to have multiplicity, and then the eigenvectors can change macroscopically. So the point I want to emphasize here is that if you have eigenvalue multiplicity, or if eigenvalues that are very, very close to each other, this can lead to instability of the eigenvectors under perturbations. And these 2 phenomena kind of feed off each other, right? If you give me a general non-Hermitian matrix, then it might have unstable eigenvalues, and then maybe they'll collide and have multiplicity. Then it'll have unstable eigenvectors, but then that'll feed back into the first issue, right? So the difficulty in this problem is if you have general non-Hermitian matrices, the eigenvectors and eigenvalues can be unstable. And it's hard to prove something about such unstable quantities. Yes. Any question?
Yeah, Professor is going to ask you something. I think it's the right time here.
Oh, am I audible?
Yes.
Mm-hmm.
I was just thinking, following on Cleve Moeller's question.
Mm-hmm.
I think you've told us that, say, the 2x2 Jordan block, you can perturb it slightly to get a matrix with well-conditioned eigenvectors. Would you tell us how to do that?
Oh, yes, yes, of course. So for 2 by 2 Jordan block, the perturbation is just to perturb the 0 bottom left entry. So if you make that epsilon, then you get something with reasonably well-conditioned eigenvectors.
I just tried that and it didn't work, but maybe I missed something.
Well, okay. So I think it depends on. I think it should work. So
I got a square root of epsilon as the condition number, but maybe I may be missing something.
you got a square root of epsilon in the
anyway,
condition
it would
number.
be good for us old-fashioned types. This would be a good way to communicate the message, to tell us what to do with that 2 by 2 Jordan block.
Right. So the general prescription, which is in this paper of Davies, is to perturb the bottom left entry. Yeah, I don't remember the details of the computation, but we can discuss it maybe after the talk. So, okay. So, wait, so there's another message in the chat.
Do you really want to continue with questions?
Okay. Let me come back to the specific issues.
Yeah, maybe
later.
It's good if you continue, otherwise.
Okay. So how do we get around these difficulties of spectral instability? So the first key ingredient is what I'm going to call regularizing perturbation. So we proved the following theorem in 2019. So the theorem says if you give me any matrix of norm less than 1 and a parameter gamma, and you take G to be a square matrix with IID complex Gaussian entries, then consider the matrix A prime, which is A plus gamma G. Okay, so you perturb A with a random matrix, and gamma is some small parameter here. Then the claim is A prime has stable eigenvalues. Okay, so if you look at A prime and you look at, so first of all, probability 1, it has distinct eigenvalues. If you look at any eigenvalue lambda I, then the distance between lambda I of A prime plus E and lambda I of A prime for an adversarial perturbation E is bounded by some small polynomial in n over gamma times the norm of E. So this exponential instability just goes away. Okay. So the summary of this is every matrix is close to a matrix which has stable eigenvalues. And the way you find this matrix is by just adding a small random complex Gaussian matrix. Okay. Okay, I see some questions. Anybody have questions about this statement?
There is a full discussion in the chat, so I don't know whom I should unmute. So maybe the last one in the Cameron. Let me look for the name. Here it is. Okay.
Oh, sorry, I didn't really have a question. I was just participating in the discussion, but I think I don't mean to derail it. I think the point is that if you make epsilon, it's polynomial in one over epsilon condition. So anyways, move on, sorry.
Okay.
Let's continue then.
Yeah. Okay, yeah. Okay, so this is the, so what this is saying is that this A prime has stable eigenvalues, and the stability is inversely proportional to a polynomial in the gamma, the regularizing parameter. Okay. And then the second theorem that we prove, which is proven, which is I guess proven in 2020, is that we can prove something similar for the eigenvectors as well. So suppose you have a matrix of norm bounded by 1 and some parameter gamma. If you add a gamma times a complex Gaussian matrix to form this matrix A prime, then its eigenvectors are also polynomially stable in the sense that perturbing A prime by E moves the eigenvectors by at most some fixed small polynomial and n over gamma times the norm of E. And we prove that the eigenvalue gaps are also inverse polynomially bounded. Okay, so this new regularized matrix has stable eigenvalues, stable eigenvectors, and large eigenvalue gaps, where stable just means that it just means that the well, it just means that the displacement of the eigenvalues is at most polynomial in the size of the perturbation. And I should say that even the existence of such a nearby A prime was previously not known. So this was a conjecture of Brian Davies. And these theorems prove this conjecture using a random perturbation. So I'll refer to such an A prime with these three properties as being spectrally stable. Okay. So any questions about the statements of these theorems?
It doesn't seem so. All is fine now. Okay.
So, so let me say a little bit about the proof of these theorems. So one of the key concepts that goes into the proof is this concept of pseudospectrum. So if I have a square matrix M and a parameter epsilon, the epsilon pseudospectrum is a subset of the complex plane. It's the set of complex numbers, so the norm of the resolvent is at least 1 over epsilon. So this is parameterized by the pseudospectral parameter epsilon. And in this picture, you have some matrix with 3 eigenvalues. So the eigenvalues are the poles of the resolvent. And the pseudospectra is just the level sets of the operator norm of the resolvent, which becomes smaller as epsilon becomes smaller. Okay, so why is this relevant? So first of all, it's a nice exercise to see that the epsilon pseudospectrum of a matrix is just the union of spectra of all matrices that you can get by perturbing that matrix by a matrix of norm at most epsilon. So the meaning of pseudospectrum is that, well, a matrix has large pseudospectrum if and only if it has unstable spectra from this equality. And so the pseudospectrum simultaneously tracks all possible perturbed spectra of the matrix. And this concept is inherently robust to errors, that if you take a matrix and perturb it, then the pseudospectrum doesn't change too much, just by the way it's defined. So, okay, so I highly recommend this book of Trefethen and Embry, which is where this picture is taken from. And the pseudospectrum, really looks different for normal and for non-normal matrices. So for normal matrices, it's kind of boring. It's just a union of disks of radius epsilon around the spectrum, as seen in this picture on the left. But for non-normal matrices, might be much bigger, which makes sense since they may have this spectral instability. So that's the pseudospectrum. And for this matrix that I showed in example 1, this is a plot of the various pseudospectra. So the eigenvalues are the black dots. The green, I guess, ellipse is the boundary of the 10 to the minus 16 pseudospectrum. And it's quite big. You can see it macroscopically. So even if you add tiny perturbations, it causes a microscopic change in the eigenvalues. And then the other pseudospectra for larger pseudospectral parameters are shown. They're bigger ellipses. So any questions about pseudospectrum?
All is quiet at the moment.
Okay. Okay, so what does this have to do with our theorem? Well, the phenomenon behind this key ingredient 1 is something we call pseudospectral shattering, and it's displayed in this picture. So on the left-hand side, I've plotted pseudospectra of a 10 by 10 tuplets matrix with a single eigenvalue of multiplicity 10. So there's a black dot in the middle of the picture. And I haven't said exactly what the parameters are, but the pseudospectra are kind of big. Okay, they're these big sets in the complex plane. And what I've done on the right is I've perturbed this matrix by a random Gaussian matrix of some small size. And as you can see, the black dots moved a lot. So the eigenvalues, which are the black dots, are now kind of all over the place. They're quite far from the original eigenvalues. But the pseudospectra with the same parameters of this perturbed matrix look quite different. In particular, if you look at the green pseudospectrum, it now consists of many small components that are far from each other. Okay, so previously it was one big blob, and now it's many small blobs. So what the phenomenon here is that the pseudospectrum gets split into many small well-spaced components upon adding a Gaussian random perturbation. And this is what we call pseudospectral shattering. And this is essentially equivalent to everything that was written in key ingredient 1 about stability of eigenvalues, eigenvectors, and eigenvalue gaps. And this perspective is the key to the proof of theorem of both of these theorems. The key idea in the theorems is to have a proof that is agnostic to the locations of the eigenvalues. So it's very hard to study the locations of the eigenvalues because they're unstable. So instead, the key idea is to study the area of the pseudospectra. Okay, so the key probabilistic idea in the proof is to show that on adding a random perturbation, the average area of the epsilon pseudospectrum of the regularized matrix A plus gamma G is small. And we're able to compute this area even though we don't know where the eigenvalues are. So that's the key idea in the proof of these theorems. So any questions about this?
No, not really.
Okay. So that's key ingredient 1. And given key ingredient 1, there's a sort of natural approach to solve the diagonalization problem, which was suggested by Brian Davies and is also similar to ideas that appear in smooth analysis. So it's going to be a two-step algorithm. So you're given a matrix A and a desired accuracy delta. So in step 1, you take A and you regularize it by adding Gaussian perturbation of size delta over 2. Okay. And then you get this matrix A prime. And by the previous theorem, by key ingredient 1, this A prime is spectrally stable. So it has stable eigenvalues, eigenvectors, and good eigenvalue gaps with high probability. So that's the regularization step. And then step 2 is that now you approximately diagonalize A prime. You don't approximately diagonalize A. And if you can do that with backward error delta over 2, then you're done, right? You've found a delta approximate diagonalization of the original matrix. And the point is that this A prime has better properties. So now for the rest of the talk, I'll discuss how do you diagonalize a matrix which is spectrally stable. Okay, so is there a question in the chat?
Just a statement by Cleve, I guess I can read it. Proof by intimidation. Talk fast.
Oh, is there a particular part that was...
Nick Refeston has got a question. Let me unmute him. Okay.
Thank you very much, Valeria. My question is, can you give us a hint at this stage of what the key difference between what you've done and what Davis did is?
Yes. So that's right. So Davies proved a theorem like the theorem above, but the dependence on n over gamma was exponential in n. So he proved something like n over gamma to the n over 2. So the difference is we are able to improve that to polynomial in n over gamma, which is, well, better for algorithms. And in terms of proofs, the difference is that his proof was deterministic. He constructed a perturbation, constructed a regularizing perturbation gamma G, which has this property, and ours is random. We use random matrix theory. So those are the differences between what we do and what Davies did.
Okay, thank you.
Any other?
No more questions for the time being.
Yeah. So this key idea is not supposed to be a summary of the proof. It's sort of the key idea in the proof. So yeah, this is not supposed to read like a complete proof of this theorem. Okay. So for step 1, you do this perturbation, and now step 2 is you have to approximately diagonalize A prime. So how do you do that? Okay, so the key, the approach in this is the key ingredient 2 is this computing the Sine function of a matrix. So this is something that was introduced by Zolotarev. So let me define the Sine function. So the Sine function of a number whose real part is not 0 is just the sine of its real part. So it's +1 if it's in the open right half plane and -1 if it's in the open left half plane. And if a matrix A is diagonalizable, we can define its Sine function to be the matrix with the same eigenvectors and with eigenvalues, which are the Sine function of the eigenvalues of the original matrix. And of course, you need the matrix not to have any eigenvalues on the imaginary axis for this. So what's shown here on the right is a picture on the top. You have a matrix with 7 eigenvalues. That's the spectrum of the matrix in the complex plane. And if you compute the Sine function of that matrix, its spectrum has only 2 eigenvalues, +1 with multiplicity 3 and -1 with multiplicity 4. And okay, you can define the sine function for non-diagonalizable matrices, but in this case, we'll only need the diagonalizable case. So we use this definition. Okay, so what's the point of this, and what does this have to do with diagonalization? So the upshot is if you can compute the sine function of a matrix, then by this, you can easily compute spectral projectors onto its right and onto the eigenspaces corresponding to the open right half plane and the open left half plane. So, if you look at identity plus the sine function over 2, you get the spectral projector onto the open right half plane. Moreover, if you can compute the sine function, then by computing traces of shifts of the matrix, you can count the number of eigenvalues to the right of any vertical line and to the left. You can count the difference between these two numbers. And so this suggests that you can do some kind of binary search and have a divide and conquer algorithm. And this is the idea of Beavers and Denman from 1974. And what they observed is that if A has well enough spaced eigenvalues, then you can reduce diagonalization to sine function computation using divide and conquer, right? You can find a line that cuts the spectrum in a way that roughly the same number of eigenvalues are on both sides. And then you can compute these projectors and you can somehow recurse. This, there's this work of Demel, Dumitru, and Holtz from 2007, which shows that all of the other things you need to do to reduce approximate diagonalization to sine function computation can be done in nearly matrix multiplication time. So you need to do, rank revealing QR factorization and other things like that, and they show you can do all. They show you can do all of these things in nearly matrix multiplication time. So for the remainder of the talk, I'm just going to tell you how to compute the sine function of a matrix efficiently. So these previous works have already shown that if you can do that, then you can diagonalize matrices efficiently. So any questions?
I don't see any. Just a comment by Cleve. It's unfortunate that the complexity world is so far from the numerical inner world, but that's life.
Oh yeah, it definitely is, and I hope they'll be closer in the future. You're right. So,
there is a comment by Alex. Alex, do you want to speak up?
Yes. So when you do this divide and conquer, how do you ensure that an eigenvalue of A prime, A dash, isn't close to the line that you've cut?
Exactly. So I will talk about that later, and that is guaranteed by the pseudospectral shattering ultimately. Yeah. Okay. So you have to guarantee that, and we'll talk about that later.
Okay, let's continue then.
Okay, so the rest of the talk is how to compute the sine function of a matrix. Okay, so how do you compute the sine function of a number? So, this is something taken from a paper of Roberts from 1972. So consider the meromorphic function g of z is equal to z plus z inverse divided by 2. And notice that this function has fixed points at +1 and -1 in the complex plane. Okay, fine. So, natural thing to try is maybe if you iterate this function, it will converge to +1 or -1. And this can be used to compute the sine function of a number. So it turns out this is indeed the case. So the key property of this function that enables this is the following. So I'm going to define a family of circles in the complex plane. So let alpha be a number strictly less than 1. I'm going to define C alpha plus to be the set of complex numbers whose distance to 1 divided by distance to -1 is at most alpha. Okay. So as alpha approaches 1, this set approaches the entire right half plane. And as alpha gets smaller, this becomes a small circle around +1. And similarly, I'm going to define circles C minus alpha to be the set of points such that the ratio of the distance to -1 to the distance to 1 is bounded by alpha. And this gives me a set of circles in the open left half plane. And the fact that these are circles goes back to antiquity, and these are called circles of Apollonius. So set of points such that the ratio of distances to a pair of points is fixed is a circle. So this is a family of circles in the complex plane. Now, the key fact about this function and these circles is that this function maps the circle with parameter alpha to the circle with parameter alpha squared. So that's a two-line sort of quadratic equation kind of exercise. So it's highly contractive in this sense. And this means that this gives you an algorithm for telling whether a number is in the open right half plane or the open left half plane. You simply take your number z naught, let's call it, and you run the iteration zk plus 1 is g of zk. And every time you do this, you end up in a circle with parameter that's getting squared. And so the kth iterate of this algorithm lies in circle with parameter alpha naught to the 2 to the k, where alpha naught was whatever the original circle was. And so what this means is if you want a delta approximation of the sine function, you run this for log of 1 over 1 minus alpha naught plus log 1 over delta iterations, where alpha naught is this important parameter. It's the circle parameter of your initial point. So that makes sense, right? Because this algorithm shouldn't work it shouldn't be good if your number is very close to the imaginary axis. And that's where the dependence on the distance to the imaginary axis comes in. So this is how to compute the sine function of a number. So any questions about this?
No, I don't think there are any questions. Okay.
Okay. So how do you compute the sine function of a matrix? Well, it's actually almost the same. So let's define a function on n by n matrices. G of A is A plus A inverse by 2. Let's assume A has no eigenvalues on the imaginary axis. And by spectral mapping theorem, the spectrum of G of A is just G of the spectrum of A. So when you apply this map to matrices, literally the same thing happens to the eigenvalues. So the iteration is now AK plus 1 is G of AK. So you take the matrix and average it with its inverse. And then, by the same reasoning, the spectrum of the kth iterate is contained in the circle with parameter alpha naught to the 2 to the k, where alpha naught was the initial circle parameter. And that means you get a delta approximation to the sine function in the sense of spectral radius after the same number of iterations. Okay, so log of 1 over 1 minus alpha naught plus log 1 over delta, which is small if your matrix has eigenvalues that are away from the imaginary axis. Okay, so this was done by Roberts in 1972. And then, so why are we not done? So this looks like we're done here. We found some way to compute the sine function. So the issue is that in finite arithmetic, this is not actually the iteration, right? So in finite arithmetic, at every step you have round off error. So you're repeatedly adding and inverting matrices, which you cannot do exactly. So really what you have is this noisy iteration. AK plus 1 is G of AK plus EK. And this proof completely breaks down. So the spectral mapping no longer holds, the iterates don't commute anymore, and it's not clear how to analyze what happens. And you can imagine that it's not even clear how to prove that this sequence of iterates doesn't blow up in condition number. Right? You're repeatedly inverting matrices and adding adversarial noise. So this is the difficulty. And there have been many previous works studying this problem. So Byers identified some cases where this does and doesn't converge. And then Bai, Demelgu, and Byers, Hay, and Merman showed that if you have a matrix such that this converges, then it gives you a good approximation of the sine function. But it was still open to actually prove that it does converge for some large class of matrices. I should say that in the Hermitian case, this is much better understood. There's a result of Nakatsukasa and Hayam, which shows that in the Hermitian case, this works. So the key difficulty is how do you prove convergence of this Newton iteration with round-off error? So, is there a question?
So the question is, what is sine of 0? How do you define it, I guess?
Oh, it's not defined. So I'm only defining this, as I said, for matrices with no eigenvalues on the imaginary axis. So if you go back to the definition of sine function, real part is not equal to 0 for all eigenvalues. So all of this is only for numbers that don't lie on the imaginary axis. So sine of 0 is not defined.
So away enough from the imaginary axis, I guess.
Yeah, I'll make it quantitative in a moment.
Okay.
I'll make it quantitative in a moment. Yeah, but you're right that sine of 0 is simply not defined. So the assumption here is that A has no eigenvalues on the imaginary axis. And that, of course, that's something we have to prevent, right? So along the iteration, we have to make sure that you never end up with eigenvalues on the imaginary axis. Okay, so so how do we solve this? So this is the situation, right? You have this noisy iteration of this function. And the key new ingredient that we use to solve this problem is what we call pseudospectral mapping. So this is the key lemma in the proof of that the algorithm works. And this is what the lemma says. It says, if you have a matrix whose epsilon pseudospectrum is contained in a circle of Apollonius of parameter alpha. So I've only drawn the circle in the left half plane. There's another one in the right half plane as well. So if now stronger assumption, if the epsilon pseudospectrum is contained in circles with parameter alpha, then when you apply this function g, so you do one iteration, you get g of a. That's a new matrix. It has a new pseudospectrum. If you look at the epsilon prime pseudospectrum of the new matrix of the iterate, then that's contained in the circle with parameter alpha squared. And okay, so we are saying that the pseudospectrum is also getting shrunk from the circle of parameter alpha to circle of parameter alpha squared, but we're paying for this. Whereas the assumption is that the epsilon pseudospectrum is contained in the circle of parameter alpha. The guarantee is that the epsilon prime pseudospectrum is contained in the smaller circle, where epsilon prime is a smaller pseudospectral parameter. So epsilon prime is roughly epsilon times alpha squared. Okay. So the pseudospectral parameter is also shrinking, but in a controlled way. So this is okay. So this is the most important lemma in the algorithm. So any questions about the statement of the lemma?
No questions. Go ahead, please.
Okay. Yeah. So in these pictures, these clouds are supposed to be the pseudospectra. So on the left, you see that they're contained in the big circle. On the right, you see that these different clouds for a smaller pseudospectral parameter contained in the smaller circle. And the proof, maybe I can show it at the end if there's time. The proof is actually, it's half a page. It's based on using contour integrals, but it is specific to this function g of z. It uses some properties of this particular meromorphic function. Okay, so once you have the pseudospectral mapping, you can analyze the algorithm. So now we revisit this iteration. Ak plus 1 is g of ak plus some round off error, ek. And now we keep track of a sequence of pseudospectral parameters along the iteration, which are shrinking, but in this controlled way. So epsilon k plus 1, which is the pseudospectral parameter at the k plus 1 iterate, is the previous pseudospectral parameter times alpha k squared, where alpha k is the circle parameter at that iteration. And what we can prove is that the kth iterate, its epsilon k pseudospectrum is contained in a circle of parameter delta for k equal to log 1 over 1 minus alpha naught plus log 1 over delta, same number of iterations, but with a stronger assumption, right? The stronger assumption is now we don't just require the eigenvalues to be in the circles. We require the pseudospectrum of the initial matrix, the epsilon naught pseudospectrum of the initial matrix to lie in the circles. Okay, so it's a stronger induction. It's a stronger assumption on the pseudospectra, and it's a stronger conclusion on the pseudospectra. And that's what allows you to do the induction. And since pseudospectra are inherently robust, this is not, we're going to be able to handle this round off error, right? Every quantity appearing in this proof is robust. And so we have to do some calculations. But if you set the, so first of all, if you do the random perturbation, that's enough to prove that at every step of the recursion, the pseudospectra are bounded away from whatever the imaginary axis is at that step. And then if we set the precision to be log to the 4n over delta, then that's enough to make sure that this proof works, basically. And that's it, right? So that implies that the spectral bisection algorithm, when you run it on a matrix which is spectrally stable, so this is the key. So the class of matrices on which it works is spectrally stable matrices, those with this shattered pseudospectrum. So when you run this algorithm on such matrices, it works. It always converges. And so that's the end of the proof. So there are two ingredients. The first is this regularizing perturbation, which is you add a random matrix, which guarantees spectral stability and well spacing of the eigenvalues, which answers Alex's question. Namely, in step 2, that's why the eigenvalues, in fact, the pseudospectra are always bounded away from these imaginary axes because of step 1. And then, yeah, in step 2, we use the keying thing is the pseudospectral mapping lemma, which analyzes the evolution of the pseudospectrum. So that's it. That completes the proof of the theorem. I make some remarks about some follow-up work. So in the proof, we actually really need to use that the random matrix you add is complex. And we wondered for a few months whether this is necessary. And then later we were able to show that it also works if you add a real Gaussian matrix. And that same result was achieved by Jan, Sine, Sani as well. So it's quite a bit more involved, but the phenomenon continues to hold for real Gaussian matrices, and we expect it will hold for many random matrix ensembles. And then there are a number of open questions. So the first question, which speaks to Nick's question, is how do you actually find the regularized perturbation? Right? So I've told you that if you add a random matrix, a number of good things happen. But actually, I have no idea how to find such a regularizing perturbation without using randomness. So that's maybe the outstanding open question for this right now. There are other questions. So one is, in our spectral stability theorem, we proved that the spectral stability of the eigenvalues is some polynomial in n over gamma. Now it remains open. We don't know whether that has to depend on n. Okay, so in fact, it was conjectured by Davies and Salinas and Herrero in '89 that such a theorem should be true without any dependence on n. And they were operator theorists. They were interested because they wanted to apply this in the infinite dimensional setting. So that's still open. And then finally, yeah, I mean, this is a theoretical work. It's far removed. The complexity bound has a log to the 6. That doesn't seem necessary. I mean, so could we bring this closer to the practical spectral bisection algorithm by improving the analysis, removing some of the log factors? And these are the references. And that's it. And actually, now I can now answer Nick's question about the Jordan block. So the question was, which perturbation of the Jordan block gives you a good condition, well-conditioned, gives you a matrix with well-conditioned eigenvectors? And I said, you just put an epsilon in the bottom left corner. And he said, well, it isn't well-conditioned. So I think what I meant to say is the conditioning of the eigenvectors of the perturbed matrix can depend on epsilon. And the only claim that I want to make is that the eigenvector perturbed matrix have a condition number that's polynomial in 1 over epsilon instead of exponential. So anyway, that's the talk. Yep. Any more questions?
Okay, so I think Volker has got a question. I'm not sure he can answer. I can ask the question himself.
No, I can. I think.
Can you?
Yeah, I think I can. I was the mic was opened. So as Cleve already said, there's a big gap between practical numerical linear algebra and the complexity results. So do you suggest that we should go and randomly perturb our whatever computational eigenvalue problem we have and then get better results? And the second question is, how far are we from implementing this into an algorithm that you can give to an engineer?
Right. So, okay. So I haven't done many experiments with this, but I would I actually would advise that if you, so the key is that the size of the regularizing perturbation in this case is related to the desired accuracy, right? And I actually would not be surprised if, even in practice, if you want to solve an eigenvalue problem with backward error delta, that it helps you to add a random perturbation of size delta over 10. More experiments should be done, but I would not be surprised if it actually improves the behavior in practice, because it does regularize the gaps. And we know that that comes into play in a lot of algorithms. Regarding implementation, so my understanding is that the spectral bisection algorithm is actually implemented in some distributed numerical linear algebra libraries due to Biedemel and Gu, or I'm not sure. So that part of the algorithm is actually the same. We haven't changed it. The only difference is that we've added this random perturbation. Now, for dense linear algebra, it's not very expensive to add a little bit of Gaussian noise to each entry. So it's not hard to implement. Of course, for sparse linear algebra, this would really blow up the cost. So another good open question, which I think is worth pursuing, is there an analog of this regularization technique that preserves sparsity?
Okay, Nick, go ahead. Nick?
Oh, well, I was just wondering if can you hear me?
Yes, yes, I can hear you.
Yes.
I lost track of how probabilities left the stage. So can you show us your main theorem again?
Yes, sure. So,
so where's the theorem?
So the main theorem is this. So it says randomized algorithm, which means with high probability. So,
you didn't say that so often, but it always means with high probability.
Correct. So this is with high probability, and then this key ingredient 1, this is also C with high probability.
Everything's with high probability. Okay.
That's right. Everything is high probability. So so that's why it would be of interest to find a deterministic perturbation, because then the probability would be 1.
Right.
So that's what I mean by de-randomized.
Okay, Bernd Beckerman. We have many questions.
Okay.
Bernd?
Yeah, thank you for the very interesting talk with lots of nice ingredients. Maybe I missed the point, but for your first key fact theorem, where you quantify the distance of eigenvalues, etc.
Yeah.
Yes. Your gamma is small typically, no? Because it should be less than delta over 2, no?
Exactly. The gamma is small.
So in fact, the new theorem is not of such a big value because you have an exploding 1 over gamma term, no?
Well, so the reason so the key is that whatever this polynomial is, this is going to go under a log, right? So we're not going to use this to. The way this is going to be used is we're going to apply the regularizing perturbation. The new matrix, the way to think about it is all relevant condition numbers of the new matrix will be polynomially bounded. So they'll be like n over gamma, right? But now when you think of what the algorithm...
Sorry.
Yes. Right, but when you think of what the algorithm, how the algorithm depends on these condition numbers, how the precision depends on the condition numbers, it's logarithmically.
Okay.
So indeed, the condition number of this matrix will be inverse polynomial in gamma, which is inverse polynomial in the accuracy. So yeah, maybe I should make it clear. By well conditioned, I just mean inverse polynomially conditioned in the accuracy.
Which for numerical people might be very large, no?
I mean, my impression is no, actually, right? I mean, I've seen many numerical papers where the accurate polynomial condition numbers are, but maybe I'm mistaken. But certainly for precision issues, if you have a, let's say, n to the 5 or delta to the 5 condition number, the number of bits of precision you need is just log of that. So it's not too bad.
Thank you very much.
Yep.
Okay, Cleve, would you like to speak up?
Yes, I would. Hello.
Oh, hi, Cleve.
I feel very frustrated by this talk. You have
okay.
You have here some of the world experts on the subject on numerical linear algebra, with Volcker and Trefethen and Alex Townsend. I'm sure you realize that. We feel I would like to sit in on a kind of summit meeting between the people that are here today and your crowd, so that we could actually, I don't know, resolve the differences between us. I mean, to me, it's very frustrating to just assume away the important numerical questions, assume that the eigenvalues aren't close to the real axis, assume the matrix is well conditioned, assume there exist eigenvectors, and then those assumptions must somehow show up in the constants involved in your estimates, your probabilities in your estimates, and it would be nice to see how those things are really work. What we learned a long time ago, we don't try and compute eigenvectors. We don't try and diagonalize matrices. If a matrix is symmetric, we'll diagonalize it. If it isn't symmetric, we'll get its sure form, its complex, its triangular form. What about complexity of the algorithms to reduce a non-Hermitian matrix to triangular form? Or we like to compute the singular values. It's a wonderful computation, and it's not. I can go on and on. I hope you get the feeling for how frustrated. The basic idea is we're all very frustrated.
Okay, so first of all, I highly agree that I would love for there to be more interaction between our fields, and I really hope we can organize something to that effect. But coming back to your question about assumptions, so actually the point of this theorem is that it does away with any assumption. So there's no assumption on A. And the claim is when you add this random matrix, you get for free these assumptions. So that's really the content, that if you give me any matrix and you add a random perturbation, then independent of everything, you get these statements. So, I mean, I can be more explicit. This polynomial is something like n over gamma to the 5. Like literally, there's nothing else in there, depending on the matrix. And so maybe the way to understand the result is, you know, it shows that every matrix is close to an eigenvalue problem that you can solve. And so therefore, it expands this idea that
no, not one with well-conditioned eigenvectors.
Yes, so right. So maybe you're right. So maybe my misunderstanding is that what I meant by well-conditioned eigenvectors is that the condition number of the eigenvector matrix is, let's say, n over gamma to the 5.
Let's say n over gamma to the 5. Now, I forget what gamma is and why is there a 5 there?
Right. So the 5 is not optimal. The key is probably.
I know it isn't, but somehow the important thing is, I mean, it's the condition number of the matrix of eigenvectors.
Correct. Right. Okay. So maybe here's a way to explain it. So, so gamma is some small number that's going to be your accuracy, right? So.
Accuracy of what?
It's going to be the desired accuracy in your eigenvector computation. Okay. So now the thing I really want to emphasize about the n over gamma to the 5 is that it's n over gamma to a constant. It's not n over gamma to the n, right? So now even if I have a very big matrix, and I set my desired accuracy to be right. If I set my accuracy to be, I don't know, some small number, the log of the condition number.
Okay, so I guess we should have let other people ask questions. We have a couple of more questions.
Okay, yeah.
Okay.
Sure, other people.
So maybe we can
I'd be happy to talk more
postpone this
after
to
that.
the coffee break. Okay. So Yuji?
Yeah, I hope you can hear me. Hi, Nikhil.
Oh, hi, Yuji.
Yeah, so I was wondering when you said in your earlier slides that your algorithm seems to improve the running time even for Hermitian matrices. Is that right? So does that mean you are suggesting that you would perturb the matrix, even if it's Hermitian or symmetric, by a Gaussian matrix, which will probably destroy the symmetry?
That's a good question. So in the proof I gave, that's what we do. But you can prove, actually for Hermitian matrices, you can prove that you get all the nice same properties if you just perturb it by a random diagonal Gaussian matrix. So what I would suggest in the Hermitian case is you take the matrix, you add a random diagonal Gaussian matrix, which is sparse and doesn't destroy the Hermitian property. And then, because there's no question of eigenvector conditioning in the Hermitian case, it's only the gaps. And then there's a result of Eisenman et al., which shows that the gaps become polynomially large. And then indeed, I mean, that's all you need to get this result in the Hermitian case. So yeah, in the Hermitian case, you don't have to destroy the Hermitian structure.
Okay, thanks.
Okay.
But you still think perturbation is necessary or helpful?
I think perturbation is helpful because, the bad guy in the Hermitian case is very closely spaced eigenvalues, right? So for example, I mean, for this algorithm at least, right? If you look at example 2, it has 2 eigenvalues that are distant something like 1 over n factorial squared. And if you add a random diagonal matrix, a small one of size gamma, then that gap becomes polynomial in n over gamma. And that's,
I think it's an issue only if an eigenvalue is close to 0 here. Wouldn't it? Because they're just dividing it using spectral divide and conquer. So the only issue is if you have an eigenvalue close to the imaginary axis for your sine function algorithm.
Well, actually, no, because remember, in the spectral bisection, you do it recursively, right? So first you cut the spectrum in the middle, and then you cut it again. So for that, you need all of the eigenvalue gaps to be large, and that's precisely what's guaranteed by the random perturbation.
Okay, thank you.
Okay, Nick?
Just a comment, actually sort of echoing something I made earlier. Nikhil, that was delightful, fascinating talk. I think to help people like Cleve and me understand better, in addition to the very general theorem, we'd like to see at the very other extreme a quantitative statement about what you do to the n by n Jordan block. So next time you do this theorem, would you include 5 minutes about what happens to the n by n Jordan block?
Absolutely. So, I mean, I can just try to say a little bit about it here. So if I were to what happens to the n by n Jordan block is something very close to this picture. So if I were to plot the pseudospectrum of the n by n Jordan block, it would be just a bunch of circles.
But of course, a very ill-conditioned eigenvector matrix by our standards, but you have different standards.
Oh, no. I mean, on the left, right? So, but then when you add an gamma perturbation, then on the right-hand side, you would get a picture that looks like this. And so so the condition number of the eigenvector matrix of the regularized Jordan block would be polynomial in 1 over gamma.
Yes, so, but it would be enormous by our standards. And that's, I think, the crux of where the communication is failing. We think that's a big number, and you need to explain to us why it's a small number.
Okay, yeah. Okay, so okay. Exactly. So I should have said this at the beginning. For me, well conditioned means the condition number is a small polynomial in n over gamma or n over delta. And that's not well conditioned in the absolute sense because it depends on the accuracy. But the sense in which it's better than, let's say, the dependence that was known before is that it only depends polynomially on the accuracy, not exponentially.
Okay, this clarifies quite a bit.
So,
Jim Denman, please.
Hi, Nikhil. How are you? So,
hi,
just
Jim.
Yeah, hi. I just wanted to mention one other comment in the chat. We already depend on randomization for this algorithm because many years ago, Cleve and I discovered a bug in QR where there was a stable two-cycle for 4x4 matrices. And there's a hack in LAPACK now that takes a random step if it detects this and then starts trying to converge again. So we all depend on randomized algorithms for the non-symmetric eigenvalue problem, just different kinds. So my question for you was, would your analysis change if your goal were to do divide and conquer for the sure form instead of the eigenvalue decomposition?
So that's a great question. I don't know. I mean, I think it's a very natural question to try to use to analyze the recursive sure form algorithm. I mean, I think the analysis. I mean, okay, the first part, what I think this key ingredient one is probably useful in a lot of different settings. But of course, the second part, this would completely change because we're using very specific properties of the sine function iteration here. So I think it's a good question. It seems to be a different question, but yeah. But I think the first part would still be useful, is my sense.
Right. I'm just thinking you might be able to make the bounds tighter since you're trying to compute, a unitary decomposition instead of a, BD V inverse.
Yeah. I think that's a great question. Yeah.
Thank you. And Daniel, would you like to make a comment that you wrote in the chat? Or?
Oh, no, this was just to participate in the chat. Thank you.
Okay, Julien, let me unmute you. Okay, go ahead.
No, same as Daniel, it was just, hi, everybody. And maybe I should say I really enjoyed the talk from Nikhil. And it's great to have some people from other communities that work on this. And I love computational complexity. So I really enjoyed the talk personally. Thanks a lot for being here.
Thanks.
Okay, so there are no more questions unless someone wants to say something and I can unmute them. And Daniel, please go ahead and.
I think there was a question on YouTube, Melina.
Oh, okay. I'm sorry.
Yeah, I should have intervened, but there was such a long discussion. So there's one question on YouTube. I'm just going to read it out. Is there a general pseudospectral mapping theorem for functions other than g of z, z plus 1 over z over 2?
So that's a great question. I haven't thought about it. So I mean, I can tell you. Okay, so the proof of the pseudospectral mapping theorem is kind of it's very. It seems pretty general. I mean, the proof is roughly here on one slide. It's you use Cauchy integral formula, you express the resolvent of the iterate in terms of the original resolvent, and then you do some estimates. Now, the only thing that's used about G here is exactly where it's, where it's, I mean, you have a clear understanding of where exactly it's analytic. So this yeah, you could try this for other analytic functions. I don't know what I think it's a good question. Yeah. Is there a general pseudospectral mapping theorem?
May I comment?
Yes, please. Yeah, you probably already know.
Well, maybe Mark Embry will echo this. My recollection is that when we were writing the book, we thought about trying to find a really nice general pseudospectral mapping theorem, and we didn't find one we liked. And I just checked, and the phrase does not appear in the book. So at least as of 2005, there wasn't a nice theorem.
Okay, so I think this answers the question, or maybe this gives a question to work on. So there are no more questions on YouTube. So I think, Daniel, you can take over.
So Cleve wanted to make an additional comment, maybe? Cleve? I unmuted you. Okay. Okay.
Yeah, okay. There, finally, I was muted. We see a lot of interest here in this community. We need two papers. One is explaining what you do to us And by us, I mean me. Explain what you're doing to me. And the other way around, we need the paper to explain what we do to you, right? And the people that understand both these worlds, like Trefethen and Demel or so on, are here and interested. I think we need this kind of summit survey, something like that.
Yeah, I absolutely agree. I think it would be great if, I don't know, if we could maybe talk about organizing a workshop or something to like really invite people from both communities and have extended discussions about,
Right.
So we can, I mean, maybe we should, I mean, I'd be happy to talk about organizing such a thing over email.
Okay. Well,
Okay,
the people from the numerical linear linear algebra community that need to be there are here today. So get some of your crowd and yeah.
Yeah, maybe I should just send an email to many of the people after, and then we can have a discussion.
Nikhil, I think I will follow up with you on this. I think it's
Okay.
it's a nice idea by Cleve, and let's see what we can do. I think it's yeah. I think there's a lot of room for further discussion.
Thanks for a lot of thanks for stimulation. You certainly got me thinking. So thanks a lot.
Well, thank you for all the questions, Cleve.
That was a very lively talk.
Yeah. Thanks also from my side. And I'm going to share the screen. Let me see whether I can do that with the okay. So that these are the next two seminar talks by Serkan Gugercin on April 21 and Madeleine Udell on May 5, before we enter the conference season, summer break, etc. And maybe even the end of the special period. Who knows?